Thank you, everybody. Thank you, everybody, for joining this distinguished webinar series. This webinar is hosted jointly by School of Electrical Engineering and Computer Science and the Center for Cybersecurity Research and Center for Artificial Intelligence Research Initiative at the University of North Dakota. It is my great pleasure to welcome Dr. Sanmukh Rao Kuppannagari, and he's going to share us his expertise on the topic titled Algorithmic Innovations for Accelerating Implementations for Artificial Intelligence. Dr. Sanmukh is a James C. Wyant Assistant Professor at the Computer and Data Science Department at Case Western Reserve University. Prior to this, he was a Senior Research Associate at the University of Southern California. He completed his PhD in 2018 in Computer Engineering from USC. He holds a Bachelor of Technology degree from IIT Guwahati in Computer Science and Engineering. His research interests include parallel and reconfigurable computing, combinatorial optimization, approximation algorithms, and AI and machine learning acceleration. He is a co-PI on 4 funded National Science Foundation Awards and 1 Army Research Office Award. He has published more than 50 papers, with a couple of them receiving Best Student Paper Awards. Dr. Sanmukh, it is great, distinguished pleasure to invite you for this talk, and it's all yours. Thank you.
Thank you, Prakash, for the kind introduction. Let me try to share my screen. Is this visible to everyone?
Yes.
Okay, good. So yeah, hello everyone. So my name is Sanmukh, and as Prakash has so kindly introduced me, I'm a professor at Computer and Data Science Department at Case Western Reserve University. And I know like a lot of you already, work on AI, have developed AI models for a variety of applications, including, I think, smart grid and various other applications. But my focus, or at least the focus in this particular talk, would be that given those applications, which very smart people like you have developed, how do we make those applications or AI algorithms run faster on, let's say, existing machines? And that's where the title of my talk comes into the picture. And the title of this talk, as well as the research lab which I'm trying to create. And by the way, a little bit background, I just joined Case Western last semester. So basically I'm setting up a new research lab here. And the title of the research lab would be what I call as AI3, Algorithmic Innovations for Accelerating Implementations of Artificial Intelligence. And I'll go into each of these terms in a few slides. A little bit of my background. So before joining Case Western, I was a senior research associate postdoc at USC, where I also did my PhD. And at the bottom here is my, let's say, previous team. I'm creating a new team here, and soon these figures will be updated. So Professor Victor Prasanna and Professor Raj Gopalkannan, they were my co-advisors. And in terms of sponsors, I've had funding from NSF, ARO, Department of Energy, and Xilinx, and so on. Okay, so before I actually start discussing what my research focus is on, I would just like to set up a stage with respect to what is the next big challenge which I see in, let's say, computing or computer science. And this is something I can define, or I'd like to define using a single word called heterogeneity. And when I talk about heterogeneity, I talk about heterogeneity both in applications, the AI ML applications which you develop, and heterogeneity in the computing systems itself. So what do I mean? Okay, I think something happened. Sorry about that. Yeah. So what do I mean here? So I'll start with heterogeneity in applications. So when we are talking about these applications or developing these applications, there is a wide variety of characteristics which is involved or required to be addressed for developing these applications. So your applications could be latency critical applications. So for example, if you are doing real-time inference for maybe self-driving cars, you need response times, which is in the matter of milliseconds. There could be high throughput applications. If you're training these large language models or CNN models, maybe latency is not a requirement there, but the throughput is a requirement, where you have this large data set which you want to go through to train your applications. Similarly, the kind of data on which your application performs, that can vary a lot too. So it could be graph analytics, where you use graph neural networks. It could be image processing, where you use CNNs. It could be time series analysis, where you use RNN, and so on. And let's say, even if we zoom into a specific application, so in this case, we are zooming into image processing convolutional neural networks. Over the years, the complexity of these applications has also increased many folds. The number of parameters has increased, the layers have become deeper, and not only that, the graph of the convolution itself has become more complicated. Now, instead of having those sequential graphs in the earlier models like VG16, now the graphs are, there is a lot of branching involved in these graphs. Let me see if I can take a laser pointer here. So there's a lot of branching which has been introduced in the newer CNN models. And similarly, new convolution algorithms have also been proposed for implementing the convolution layer. So for example, there's this algorithm called frequency domain convolution. Im2col is the most basic, which we deal with whenever we are doing something in PyTorch. There is Vinograd, K-ary, depth-wise convolution, and so on. And even now, even this year, there have been a couple of more convolution algorithms which have been proposed by the community. So in that sense, the problem space of what is the, how do you select these algorithms? How do you select these various models? All that just increases exponentially. And that is what I mean by heterogeneity in applications. The wide variety of choices which we have, the wide variety of requirements which we need to address. This variety is what we define as heterogeneity in applications. Now, the second dimension here is the heterogeneity in the computing systems itself. Basically, these are the systems on which our AI/ML model will be running. And these systems are also observing heterogeneity because of the following reasons. And the main reason is the rise of what we call as domain-specific accelerators. So for example, in case of AI, if you have heard about custom AI accelerators, these are these ASIC chips which are made to accelerate AI, or even some of these newer GPUs which have tensor cores or tensor processors. They can also be considered some sort of a domain-specific architectures because they are customized mostly for AI applications. And similarly, for signal processing, there are the signal processing accelerators, and there are a variety of such accelerators exist. And the reason for this rise of this domain-specific architectures in the recent years is because of the following 3 points. This is something which was mentioned by John Hennessy in his talk. And the reasons are as follows. The first reason is this end of Moore's law. Now, the density of the transistors on the chip is no longer, doubling, let's say, every 18 months or 1.5 years or so on. The second is what we can call as reaching the end of Amdahl's law. So, I mean, if you have taken any computer architecture course, you might have studied a little bit about out of order processing and how we can extract, maximum fine-grained parallelism out, or instruction level parallelism out of your program. But that is also reaching its limitations, and we are almost at the end of getting or extracting performance using that kind of optimizations. And the third reason for the rise of domain-specific architectures is because of a shift in the application focus itself. So, previous to, let's say, the proliferation of AI/ML models, most of the driving forces in computing systems was HPC kind of an application. So you would like to do these large simulations on some scientific data set. But nowadays, the application focus has shifted towards more individual IoT-enabled devices, and these are all data-oriented, where you need to perform this analytics or AI/ML models on, let's call it a streaming data in maybe in a real-time manner or a high-throughput manner. So the application has become much more data-oriented or much more individual device-oriented. And because of all these reasons, we are seeing in a rise of a variety of domain-specific architectures, and that is leading to a heterogeneity in computing system. So if we look at a few characteristics of heterogeneity here, we can look at power. There are these data center devices versus edge low power devices. The type of programming paradigm is also different. You have general purpose, or you have vector. You can think of it as GPUs. You can spatial. You can think of it as FPGAs. And even in terms of technologies, there's a wide variety of technology which is being used. There are these optical neural networks, optical processors, ASICs, reconfigurable processors like FPGAs, and so on. Now, from an AI system designer point of view, this heterogeneity in applications as well as this heterogeneity in computing systems is a nightmare, because it's simply infeasible for us or for an AI system developer to take an application and with all its characteristics and try to map to each and every device, basically perform this customization to map to each and every device, because there are just so many combinations possible. So it's essentially a nightmare. And that is where my vision comes into the picture. This is something, I'm a big Star Trek fan. And so, this is where my vision is inspired from. So if you have seen any Star Trek or in general, any sci-fi, so usually what happens is that the engineers or the scientists there, they simply tell the computer that, okay, I want some problem to be solved. And the computer in itself determines what is the problem to be solved and how best to allocate the computing resources to that particular problem. And that is what ultimately my vision is, that can we do something similar, that can we abstract away the mapping of the applications or the mapping of the problems to the underlying computing systems without a AI system engineer or computer engineer having to worry about the capabilities of the computing systems as well as the heterogeneity of the applications. So in this case, let's call it the first baby steps which I am following here would be what I call as algorithmic innovation for accelerated implementations of artificial intelligence. So the idea here is that my main focus is on performing these algorithmic or device agnostic innovations, something which can be ported to multiple devices. To achieve the objective is accelerated implementations, because we want a high throughput AI model training, or we want low latency AI model inference, or so on. Everything can be considered as accelerated implementations. And finally, the domain in which I'm currently focused on is the artificial intelligence. So I saw the chat. Yes, if you have any questions, maybe you can raise a hand or unmute yourself or just put it on chat, and I can answer anytime in the presentation. So you don't really need to wait till the end of the presentation. Okay, so in terms of research directions, there are 3 broad areas which I am in general interested in, and some of these areas I have already worked on. So in terms of algorithms, I have focused on developing combinatorial algorithms for design space explorations, and these are typically NP-hard problems, also algorithms for online strategy selection. In terms of actual applied data science or actual applied AI ML, the one thing which I would like to focus on, and I'm setting up a team for that, is how do you do this performance modeling of computation to this hardware mapping, or come up with some deep reinforcement learning or graph machine learning algorithms for optimal computation to hardware mapping. And similarly, finally, the third category would be the AI hardware and system development, where I would like to develop some of these custom architectures for AI ML models. So for example, deep neural network or deep reinforcement learning, privacy preserving CNNs, and so on, or some novel approaches to DNN like locality sensitive hashing based DNNs or second order neural networks. Here are a few illustrative problems which I have been working on in the past few years. So in terms of reinforcement learning accelerators, we developed a framework for scalable reinforcement learning and proximal policy optimization. It's again a deep reinforcement learning algorithm. In terms of convolutional neural networks, we came up with a polynomial time complexity solution for CNN task graph mapping. It typically is, it's NP hard, but we showed for certain cases of CNN graphs that it can be, we can come up with a polynomial time complexity algorithm. Then we also looked at HE-SPA. So HE is homomorphic encryption. Basically, these are privacy preserving neural networks. And so we came up with how do you perform privacy preserving neural network using sparse convolution, and we modeled it as a maximum bipartite matching based scheduling problem. And similarly, we were also looking at packing. This is one step which is performed in this homomorphic encryption convolutions. And we are currently looking at modeling this packing problem as vector bin packing problem. So these are some of the illustrative problems. If you want to understand, or if you are interested in any of these, just, you can send me an email and we can set up a meeting and discuss these in more detail. But what in this talk I will do is I will take one problem and I'll try to explain how I or my research team approaches these problems and tries to come up with a solution for that particular problem. So this problem is what I call as parallel actors and learners, a framework for generating scalable reinforcement learning implementations. And it was published in 2021 in HIPC conference. So just a little bit of a background. So in terms of reinforcement learning, so if you recall, if you have taken any course, so what usually happens is as follows. So we have this agent. So in this case, let's say this agent is a robot. That robot has a worldview or a model of the world. And what this robot does is that it interacts with the world. That means it takes certain actions. And depending upon what action the robot has taken, it receives some experience from the world. And given this action, given this experience which it received, the agent stores it into this data set. And then there is this another parallel update step, which we call as learner. And what happens in this update step or in the learner is that the learner samples from this data set, which if you recall, collects actions and experience. So it performs this sampling and it updates the worldview model. And this worldview model is again used by the agent to interact with the world. So this is kind of like a closed loop which is going on in this deep reinforcement learning models. So again, going a little bit deeper. So if we are looking at this worldview, typically, if we are talking about deep in the deep reinforcement learning, this worldview is represented using a neural network. It could be dependent upon your domain. It could be image. It could be, a simple ANN. It could be some sort of an LSTM. So, we can decide what model to use here depending upon how the domain looks like. But let's say you have this worldview model, which is a neural network, which given a state. So in this previous diagram, the state is basically, what the world looks like at any given point. Given a state, this neural network outputs an action. So this action is something which the agent actually executes in the environment. The environment gives back an experience. The experience, you can think of it as a reward and the next state of the environment. And so this state, the current action, and this experience, which is essentially this R and S, is stored into the data set. And from this data set, we go back and we can update this neural network. So deep reinforcement learning has shown widespread success in a variety of applications. If you have heard about AlphaGo is essentially a deep reinforcement learning algorithms. Even in terms of robotics, deep reinforcement learning has shown widespread success. Even in building HVAC control, so in smart grid or cyber physical system applications, again, deep reinforcement learning has been very successful. But the problem with deep reinforcement learning is essentially training. The training these RL agents is extremely time consuming because there is this large state space which needs to be explored, and that becomes a computational bottleneck. So if you are looking at some of these famous algorithms, so for example, if we are talking about this AlphaGo 0, it takes us about 10 to the power 1 or 10 to the power 2 days to train these kind of a model, basically several tens of days to train an AlphaGo 0 model. But one can argue that, okay, maybe, this is something which these big companies like Google has trained to demonstrate something. And this is not what we as researchers usually focus on, which is a valid point. But if we are looking at some of these models which we as researchers focus on, so for example, Mujoko or Atari, these are typical benchmarks which are used by RL researchers to develop or test their algorithms. Even for these, let's say, benchmark, it takes several hours or almost as a day or a couple of days to train these reinforcement learning algorithms. And just think about the iteration time it would take for a general researcher to come up with a new advancement in the RL algorithm, and just then you simply run it on a single Atari game, and it takes you an entire day or 2 days to just test whether that algorithm is correct or not. And you ideally, if you want to publish a paper, you should be doing it for some 10 different benchmarks and 10 different configurations. So that's simply, it's extremely time consuming, and that is a real challenge here. And that's why we are like, can we do something? Can we accelerate this AI so that we can reduce the iteration time for this algorithm developers? And that's where our research here comes into the picture. And so for that, we first talk about what a general reinforcement learning paradigm is, because ultimately this is an abstraction which we will need before we can come up with any framework which can perform this scalable RL deployment. Because recall, ultimately the idea here is we want to do this device agnostic algorithmic innovations. The another reason being there is that if someone is coming up with a new reinforcement learning, they should be able to use a framework without any customization, let's say. So we look at what this abstraction is for the general reinforcement learning paradigm. So we have the actor, we have the environment. The actor observes the state from the environment, and the actor performs an action. And this action is performed by looking at the neural network. From the environment, we receive the experience, the reward, and the next state. That experience is stored into a data set, and that data set is called prioritized replay buffer. I'll explain in a few slides why this is called this. From this replay buffer, there is a learner. That's a different process, a parallel process, which samples multiple data sets or experiences from this data set, and it performs the weight updates of the neural network. Basically, it's updating the neural networks. And then there is, let's call it a weight synchronization step. So basically, the learner updated these weights, and the same weights need to be reflected into the actor. so that the actor can take the actions in the environment. And in general, we usually have multiple parallel actors interacting with multiple parallel environments. So, in reality, when we are training these RL models, these environments are typically simulators. So you can have these multiple parallel environments running on your, CPU or, computing system. And similarly, you can have multiple parallel learners who are doing this parallel weight updates, and then you synchronize everything, and then you bring it back to your actor. So in this particular work, our main focus is on implementing this prioritized parallel replay buffer. Everything else, there are already existing solutions which can be improved, no doubt, but that's not something which we have focused on. But in this work, we are just focused on how do you scale or efficiently implement this prioritized replay buffer. So let's look at how this particular abstraction maps onto an actual hardware. So in terms of hardware, this is a high-level abstraction which we have. So we have these actors, we have these learners. The actors, or even before we go there, the actors interact with the environment. The environment is something which we put on CPU. And the reason is that these environments are physics simulators. And it's extremely difficult for us to come up with accelerated versions of these environments. So that's something we thought that, okay, maybe CPU is the good option here. Now we go into the actual actors. Given that these actors are tightly coupled with the environment, that means there is always this communication of state and action. Typically, we always put these actors on the CPU itself, and the other components of our the general reinforcement framework is these learners, and these learners are something which we map onto the accelerator. And what these learners do is that they sample it from this replay buffer, which currently in this abstraction, we are putting it on CPU. We'll discuss in the next few slides. These learners sample it from this replay buffer. They learn, they update the gradients, and they update something called a parameter server, which has all the weights. And these parameter server, all the weights are synchronized with the weights of the actors. Now, given this particular overall reinforcement learning paradigm, let us zoom into this replay buffer, which we also call as parallel prioritized replay buffer. We add parallel because there are these parallel learners or parallel actors which are inserting data or sampling data from this replay buffer. So what does this replay buffer do? So if we look at the objective function of a reinforcement learning, this is what an objective looks like. So let's say this was the current state and current action, and this is the output of the neural network which we had. It gives you Q of S comma A. Q is some value, the quality function. And let's say you took this action A of I in state S of I. If you recall, the environment gives us this reward Ri, and it gives us the next state Si dash. So given Ri and this next state Si dash, what we do is we look at our neural network again, and we try to find out what is the maximum utility of the state Si dash, and we add that to Ri to achieve the maximum or updated utility of the state S of I. So it's a sequential decision making. Essentially, what we are saying is that we took in state Si, we took action Ai. So the updated value or quality of the state Si would be whatever reward we received and the quality function or the value of the state Si dash, where we ended up by taking this action. So this difference here is the extra information which we gained, and using this information, we need to update our neural network model. And to achieve this, what we typically, or what these reinforcement learning algorithms typically do is, hundreds of samples, because you have these parallel actors. So hundreds of samples typically get inserted into your prioritized or replay buffer. From these hundreds of these samples, we want to sample experience with probability proportional to this particular error, which is also called as TD error. And the reason here is that the higher the TD error, the higher is the information gain. So for example, in this case, if this subtraction was 0, that means you are not gaining any information because of this particular operation. But if this minus was a very large value, that means this Q value needs a major update, and that's something which you should be focused on. And so that's the reason we sample the various experiences from this replay buffer using priority, which is defined by this TD error. So again, this recaps the same thing, that the data with higher data or samples with higher loss should be updated more frequently and sampled with probability proportional to the loss. So the key operations that we need for our replay buffer are insertion. That means you're doing a priority update and data insertion. You need sampling. We need to sample according to the probability distribution. We need priority retrieval, priority at index I, and we need priority update, which is update priority at index I. So before we go there, let's quickly talk about how we are doing this sampling. So sampling is essentially you want to sample using a probability distribution, which can be performed using what we call as inverse transform sampling, and it works as follows. Let's say on x-axis, you have your discrete values. In our case, it's a discrete value. So these are on this x-axis, we have all the samples experience, which we want to sample. On the y-axis, we have values between 0 to 1. And you randomly generate a value using uniform distribution between 0 and 1. And whatever value you obtain, you simply take the value which is under the curve corresponding to that value. So for example, let's say this value is something like 0.76. You go straight into this curve and you try to find a value which is just below this, this particular point on this curve. And essentially, this is a prefix sum of all the values which are below this particular point. So basically, you're taking a prefix sum of all these values, and as soon as you reach a value such that the prefix sum is equal to this particular value, you say that this is the value which we need to sample. Okay, so basically the problem of sampling from the probability distribution boils down to finding the minimum index whose prefix sum is greater than u. So it's a classic prefix sum problem. And what typically the state-of-the-art works have done is they have implemented this prioritized replay buffer using a very simple, naive array-based representation. And in array-based representation, usually the priority update and retrieval takes order 1 time. And if you want to sample, it will take something like an order in sample or even insertion. It takes something like an order n time, because you might have to go through the entire array and find this prefix sum and try to find out what is the best best variable which you want to best experience which you want to sample. So we had some ideas of what is the data structure which we want to use, but even before that, one sanity check which we have to do is we need to see if replay buffer is indeed something which is worth optimizing. Because let's say if it spends, if the algorithm or reinforcement learning algorithm spends less than 10% of the time on replay buffer, then it's just not worth optimizing. So what we did was we just implemented the replay buffer using the existing frameworks, and we just did some profiling. And what we realized was as follows. So in this particular scenario, we performed 2 types of mapping. First mapping is what we call as CPU GPU, in which your actors and replay buffer is on the CPU and the learner is on the GPU. And second is what we call as GPU based mapping, in which case the actor is again on CPU because the environment has to be on the CPU, but the replay buffer, we moved it onto the GPU. So this slide shows the first implementation. That means the CPU GPU, your replay buffer is on the CPU. So in this case, what we see is that there is these 2 items, which is corresponding to priority update and prefix sum index. They constitute the majority of the execution time of our entire reinforcement learning algorithm. So that means that any optimizations which we do for replay buffer is expected to reduce the overall training time significantly. So that's something which we should pursue. Now, but then again, the second option is, before even coming up with any novel strategies or any other innovations, what we thought that why not we just take this replay buffer and just simply put it on GPU. That's the second mapping which I talked about. So in this case, we took the replay buffer and put it on GPU, because usually most of the time that's the best solution. It always works because of the computation power of GPU. So in this case, we did see a reduction in the total execution time. So if you look at the CPU GPU mapping, the execution time was 12, but in this case, the execution time was somewhere around 6. So there was a significant reduction. But now the problem is, or not a problem, it's an opportunity, that even in this reduced execution time, a majority of portion or a significant portion is still being consumed by replay buffer. So if we are able to optimize this replay buffer, then definitely we can it can provide us with significant performance benefits. And one of the reasons, or a couple of reasons why this is happening, or why replay buffer is taking a significant amount of time in execution, is because of the low arithmetic intensity of replay buffers. That makes it a memory bound problem. There will be a lot of transfers between CPU and GPU. And the second is high access level latency of multi-level memory hierarchy. So typically, as a rule of thumb, GPUs are very good when you are performing dense high arithmetic intensity operations with low transfers between CPU and GPU. But in this case, that is not what is happening. And so replay buffer performance suddenly becomes a bottleneck. So in this case, what we did was we proposed this data structure called, not proposed, we used this data structure called K-ary sum tree. It's a data structure which is already existing. But we made this connection that this is a very nice data structure which can be used to solve this particular problem or implement this replay buffer. And the idea of this K-ary sum tree is that at the value of the parent node is the sum of the child node. So if you are looking at any of this parent node, the value of this is the sum of all this child node here. So if you are looking at this leaves here, let's say at this leaves, you have this actual experiences with these probabilities, the TD errors. Then the second level here, the parent of these 4 leaves would simply have this value, which is P1 plus P2 plus P3 plus P4. And this is how you construct your tree, where in each intermediate level, the value of that node is basically the sum of all the children below that node. And there is one parameter for this tree, which is the K, which defines this Fanout. In this case, the Fanout is 4. And in this particular K-ary sum tree, the priority retrieval comes out to be order 1 if we can directly retrieve from the leaf node, for which we simply use array pointers in this particular case. But if you want to do a priority update, so let's say you have this sample in which the node's priority or the TD error was improved. In that case, the priority update needs to be propagated from this last level to the root, and that comes out to be an order n to the base k operation. Basically, you have to travel and update each of these nodes, in the intermediate nodes, till you reach the root. In terms of sampling, the complexity comes out to be k log n, and the reason is as follows. So when we are doing sampling, we are essentially computing this prefix sum. So what we do is as follows. We start with the root, and as we recall, the root has the sum of all the first level, or in this case, the level 2 nodes. And depending upon what value we are searching for this prefix sum, we look at all these child nodes and we decide which node is it that we want to go. So for example, let's say in this case, maybe at the root, the sum of these 4 values is 100. And let's say this is evenly split. This is 25, 25, 25, and 25. So in this case, if our value is something like 80, then we will say 80 is greater than 25, 80 is greater than 25 plus 25, which is 50, 80 is greater than 25 plus 25 plus 25, which is 75. And so we will go into this rightmost node, which is P2, 4 in level 2. In the level 2, again, we will repeat the same operation. We'll go through all the child nodes and see in which node we have to go down. And we'll keep on going down till we reach the leaf. So at each level, we are exploring all the k children. So that's why we have this factor of k. And there are log n to the base k levels. So that's why the overall complexity comes out to be k multiplied by log n to base k. So that's the sampling complexity. So if we compare just the theoretical complexity analysis of K-ary sum tree with the naive, the state-of-the-art implementations of replay buffer, it comes out to be as follows. In terms of insertion, we increased the complexity. It became log n to base k compared to 1. In terms of priority retrieval, it's the same, order 1. In terms of priority update, it is again increased log n to base k versus order 1. But in case of sampling, there is a significant reduction, because in sampling, we have k multiplied by log n to base k versus order n. And this n is usually typically very large. It could be as high as millions of tens of millions. So in terms of impact of this k, if you have a larger k, then you will have this lower number of layers, but your sampling complexity will also start increasing because of this factor k, which is in the multiplication. Another aspect of this, let's say, K-ary sum tree is what we call as synchronization. So if you recall, there are all these various nodes, and if we are updating, let's say, this particular node, in this case, we need to update all these nodes which are above, which are basically the parent of this particular node. But what if we are also updating, let's say, this particular node here, or, we go from here and there is this node which also has to be updated. So in that case, we have to update this node, but we will also have to update some of these nodes which are common to these two paths. And in this case, we do need some synchronization. So, and the idea or objective of the synchronization would be to minimize the time when we are holding any of these locks. So, if we are doing synchronization, we usually implement using this locking mechanism. And, the most naive approach could be you lock the entire tree, which is obviously none of us will be doing it. So another aspect could be you put locks at each of these node level granularity, or another option could be you put locks at each of these individual levels. But in general, what we realized using, experimentally is, and even, by intuitively, is that if you have two separate locks, for in this case, level 1 to 5, there is a single lock. For level 6, there is a separate lock. So if you use two different locks for, all the intermediate levels and the final level, that usually is good enough for us in terms of performance. And in terms of actual accuracy, so one thing to realize is that if you are using just these two locks, it does not guarantee full accuracy. But because this is ultimately a data-driven, reinforcement learning algorithm, experimentally, what we have shown is that in our paper, that this does not impact our accuracy, because ultimately we are dealing with a lot of these approximate computations. Then the third aspect of our problem here is design space exploration. So if you recall, the first aspect was we started using K-ary sum tree. The second is the synchronization locking mechanism. But the third is, how do you determine what is the best value of K? And how do you determine how many actors and learners this particular value of K can support? Or it could be the other way around too, that if, let's say, you are given the number of actors and number of learners based on, let's say, your computational capabilities, how do you define what is the best value of K, or what is the best ratio of actors to learners, so that, your entire pipeline is balanced? So in this case, we started trying to perform this modeling analytically, but that's something which we were not successful. And basically, we simply did some profiling. But an open question is as follows, that can we do this better? Can we come up with some analytical or data-driven model which can tell us that for this particular reinforcement learning algorithm and the underlying computing platform, maybe the CPU as well as the accelerator, can you tell us what is the optimal ratio of actors to learners, as well as the optimal value of K for that particular problem? So that's an open problem which we will be solving in future work. Now, given this particular, let's say, the technique or the approach which we developed, this is how we perform the experiments. So for baseline approach, we used the Ray RLF. This is something developed by UC Berkeley, and it is used for implementing this reinforcement learning algorithm efficiently. And the questions that we wanted to ask in our experiments were as follows. The first is that, what is the impact of Fanout K on the performance? What is the performance of a proposed synchronization mechanism, the two different locking mechanism? And what is the performance when our optimized replay buffer is plugged directly into the existing library? Because note that ultimately our objective is to have this general scalable reinforcement learning algorithm. But if we come up with our own specified implementation of this RL library, that defeats the purpose. So in this case, if we can simply plug in our replay buffer into RLlib, and if the users can simply use that updated RLlib, and that's a good enough, that's a, I would say, very enticing solution from our point of view. So to answer the first question, what is the performance of replay buffer operations versus Fanout? So we can see three different operations here. So if you are looking at insertion, if you are increasing the Fanout, the insertion complexity decreases because insertion is simply log n to base k. In terms of sampling, if you are increasing the Fanout, initially it decreases, but when the capacity, the value n of your replay buffer, when it starts increasing, you suddenly see a local minimum. So after some point, what happens is, if you increase the Fanout, the complexity or the total time for your replay buffer, it starts, total sampling time in your replay buffer, it starts increasing. And finally, the total time, which considers sampling, insertion, on all these other operations, it also sees a similar dip into the operation, that when we are increasing this Fanout, we see this kind of a dip, where if you are increasing this Fanout, you suddenly start seeing an increase in the total time after a particular point. So, in summary, if you're talking about insertion latency, it decreases. If you're talking about sampling latency, it decreases up until some Fanout value, K, and then it starts increasing. And if you are talking about this total latency, it again has a somewhat similar, let's say, pattern, where it decreases up until some point and that it starts increasing. And usually this local minima is somewhere around the Fanout of K is equals to 8 or 16. And this is for this particular problem. And if you change the problem, if you change the number of factors and learners, these numbers could change too. In terms of optimized synchronization, that means using two locks, which is what we call as optimized. So we perform the following comparison. So first comparison, the blue line here is the global log, which is something which no one will use, but we just wanted to, see how our algorithm performs against that. So clearly against the global log, we see a significant reduction, but that's not our claim to fame. Our claim to fame is compared to this no log solution. So in no log, what we are doing is we are not using the logs at all. So basically there will be a lot of this erroneous results. And in this case, compared to this no log scenario, our optimized scenario has, it has a higher execution time, but that execution time is, at least for the smaller number of cores, is not too bad. When we increase the number of cores, the execution time starts increasing. But the point here is that our optimized solution, in terms of actual accuracy, it's not too bad against the accuracy which you could obtain using a global solution. So basically, in terms of accuracy, we are close to what this global solution which get. In terms of performance, we are close or pretty close to what this no log solution would get, at least for the lower number of cores. For higher number of cores, we start performing much worse than this no log scenario. In terms of performance improvement over state of the art, that means this is the scenario where we are plugging in our prioritized replay buffer into the existing framework RLlib. What we saw was that we were able to achieve almost 1.2x to 1.7x speed up in the overall reinforcement learning training. So we are not just focused on the prioritized replay buffer optimization or execution time. We are focused on the entire reinforcement learning training. So in this case, we considered the algorithms, deep Q network and DDPG algorithms, and this is how the particular graph looks like, in which case we are getting this significant reduction, although this reduction starts decreasing when we are increasing the number of cores or number of actors or learners in our system. So if we were to recap this particular problem, the approach which we followed is as follows. So in terms of algorithmic innovation, we use this K-ary tree data structure for replay buffer, and we relax some of the synchronization primitives. In terms of accelerated implementation, our target was a CPU plus accelerator platform, in this case GPU. And in terms of artificial algorithm, this was a deep reinforcement learning algorithm. It could be any of the deep reinforcement learning, like we showed DQN and DTPG. We can also use PPO and some of these other algorithms. Basically, any deep reinforcement algorithm which needs a replay buffer. And in terms of future direction for this particular problem, I will be looking into what I call as extreme scale replay buffer, that if you have a cluster with a large number of accelerators, how do you implement this replay buffer in a scalable manner? So for example, if you look at this graph, if we are increasing this number of cores, the total improvement has started to decrease. But if you want to do it on a big cluster in which you could have hundreds of parallel actors, how do we make sure that we are still able to achieve the scalability results that we want to achieve? So that's one thing which I would like to focus on. And the second thing is something which I alluded a little bit before, that how do we perform this design space exploration, or how do we develop an analytical or data-driven performance model, which can help us in performing predictive analytics to determine optimal actor to learner ratio, as well as the optimal value of the Fanout K. And with this, I would like to thank everyone for listening. And if you have any questions, just feel free to put it on chat and ask me.
Thank you, Dr. Sanmukh, for your time. We'll take questions now. If you have any questions in the chat, could you please populate the question? If not, let me start the first question. So I think it's very interesting on how you and this accelerated focusing on this reinforcement approach on how we can speed up this computational run. But my question is, how do you rank between the data transfer and priority update? Are these two are the bottlenecks where you see, I'm not sure, how you rank these chunk of block, which is actually more priority to you. It looks like, the priority update is a very interesting or challenging task, because as the size of the tree is actually increasing. So
Yeah. So let me see. So ultimately, if we look at this particular graph, so we have these two important, even before we go there. So usually when we are talking about this reinforcement learning algorithms, so when we are doing this forward backward propagation, that's our actors and learners. And because of the power of GPUs, and like I mentioned that these actors and learners are typically extremely dense operations. So this forward and backward propagation, this number just keeps on decreasing with newer GPUs, with newer algorithms. So now these two terms, this priority update and this prefix sum index, these are the two terms which start becoming the bottlenecks. And in this particular case, to your answer in terms of data transfer, it includes both. These two terms includes the data transfer between GPU and the CPU for the replay buffer management, and it also includes the time of your the pointer mapping for traversing through the tree or through your the K-ary sum tree. We do not look at least I don't think we put these numbers into the actual paper regarding the split between data transfer and traversals, but usually from our experience, data transfer is typically very low because you are simply transferring the S, A, and S dash, which are like, I think, maybe around 16 bytes or something. It's a very small value which gets transferred. But the problem happens when we are doing this traversal, the priority, not the priority queue, in the replay buffer, because these replay buffers have like something like millions of nodes. And when you are doing this traversal, you start hitting a lot of these cache misses. So in that case, I would argue that the communication portion would be much less than the traversal portion of replay buffer.
Thank you. Any other questions? So we can. Nirup, do you see any other questions on your end?
No questions yet. I'd like to encourage the participant list to ask any questions to Dr. Kuppannagari.
Well, let's see while we wait for. So how do you see non-reinforcement learning approaches? How do you take this CPU, GPU kind of thing, what you do, and I know this is geared toward this reward mechanism,
Yeah.
And I'm just curious to see, I think we have a question from David, who's our faculty. Dave, do you want to go ahead and maybe and ask the question so he can answer both?
Sure. I'll also point out that in the webinar chat, it's disabled. So if that can be enabled, more people might post a question.
Oh, okay. I did. Thank you. Yeah.
I'm interested in data movement and the cost that has on performance. I'm wondering if do you anticipate when you go to large numbers of GPUs that data movement is going to be something you're going to have to focus on to maintain the same scale of performance improvement? Yeah,
definitely. So I mean, that's why when I talked about that extreme scale,
yes,
that's one of the reasons that you have so many, let's say, parallel actors running on a cluster, and now when suddenly all of these actors try to sample using, let's say, a replay buffer, that will start becoming a bottleneck wherever you have that parameter server. So that's something that has to be, or at least explored. Unless I do some profiling, I cannot, concretely tell you that will become a problem or not. But that is something which has to be explored because it can easily become a bottleneck.
Yeah, I would anticipate there's going to be
definitely
some performance hit.
There will be a performance hit, definitely. Although one, let's say, silver line, which I would say here is that, so if you look at, this particular paradigm where you have a parameter server, which is replay buffer, it's not too dissimilar to what happens in distributed training of machine learning models. And in distributed training, a lot of this communication happens in terms of the actual weights which are being transferred, which is much larger than the sample sizes which we are transferring in case of the replay buffer. So that is one, I would say, a silver lining, but that doesn't exclude us from considering communication problems or problems which communication can give us.
I agree. Thank you very much.
Okay. Let's see. Hopefully the chat is enabled from others. There's two options. They can either raise hands or maybe they can also put some questions on chat. But very interesting work, Dr. Sanmukh. Thank you for spending your time today with us. Are there other techniques other than just looking at K-ary sum approach, because it's I'm just curious because sum of all child nodes is it's sometimes simple as powerful as we think and look at it, but I think I'm just curious to see, I'm not sure about in this area there must be some other way also to look at modeling this propagation of leaf nodes.
Yeah, definitely. So we chose K-ary because the probability, the sampling model was, it fit neatly in terms of prefix sum. But I mean, definitely, I'm assuming, this could also be a good opportunity for people to use hash tables or, locality sensitive hashing or things like that. That's something which we haven't explored yet, but yeah, definitely, I think I would like to explore that too and see, maybe we get even better performance and maybe, maybe we solve this problem of communication using, that kind of approach. So I don't know. I'll have to think more about it. I think there is.
Cool. Nirup, do you see any questions?
No questions on the chat, but I believe Eric had a question to ask. Eric?
Well, if not, I think, what we could do is we can have Dr. Sanmukh's email, so we'll post it on the website as we share the recording, and people can always reach out to him for the questions if they have any. But in the interest of time, but I think I'm going to thank Dr. Sanmukh for his talk today, and we look forward to our collaborations, and thank you so much for spending your time again. And as a token of appreciation, we'll send you a nice plaque from our UND campus signed by our dean and our directors, so thank you again for your time.
Yeah, thank you so much. It was great giving the talk, interacting with you all.
Yeah.
Yep. Thank you.